It is my greatest pleasure that we can welcome you back to the videos of Crystal Clear Electronics. Ambrus, we can see a small model aircraft in front of you. I suppose you brought this with you as a personal item to show us. What do we need to know about it?
Yes, this is a scale model of an Airbus A350 twin-engine aircraft, as you can see here. I love airplanes for many reasons, chief among them being their status as a symbol of human engineering excellence. It's enough just to think about how mechanical engineering, electrical engineering, and the software side are all intertwined here to form one big unit in the form of an aircraft. And just think that in such an aircraft there are more than 500 kilometers of wiring representing the electronics side. You can also think that, as you can see, this one has only 2 engines. Not long ago, only aircraft with 4 engines were allowed to fly across the ocean. But today, they can guarantee safe operation to such a degree that even with 2 engines, the chances of both engines failing at the same time are virtually zero, and even the chance of one engine failing is pretty low. You are guaranteed to make it from Europe to America. That's the level of engineering knowledge, and it really manifests itself in the form of aircraft. I used to have some work that was connected to aircraft. One of them was even linked to robots and aircraft at the same time. It was about a small company and us developing a flight simulator that you could sit in. You were surrounded by a bunch of screens, there was a yoke, and the robot had to move the person in the simulator depending on how they moved the yoke. This is important so that when you intervene, the movement of the plane not only changes the image, but also gives you a feel of what it's like in a real plane. It's designed to be used for training and all sorts of purposes. The other aeronautical work was about a small electric aeroplane. The aim was to develop an aircraft that was purely electric, meaning that it was powered by batteries. And, of course, with aircraft we said that reliability was very important. Here, the task was to test the electronic components that manage the operation of the batteries against mechanical shocks and impacts. So we had to make sure that no problems occur up to the specified operating hours. And, well, in the beginning, there were 1 or 2 ICs or capacitors that came off the PCBs, but then of course the electrical engineers fixed that, and all the electrical components in the aircraft were now fail-safe.
Thank you very much, it was very interesting, especially since batteries can make this topic related to power supplies. Seeing how important it is, let's get back to our power supplies. Knowing the definition of power supplies and the output characteristics, we continue with Ambrus to review the input characteristics and efficiency of the power supplies. The floor is yours.
Thank you very much, Danny. In the first video, we learned that the 3 main characteristics of a power supply are input, output, and efficiency. We also now know that the output voltage of a power supply can vary depending on the electronic device connected to it if there is no regulation. Now, let's look at the input characteristics and efficiency of power supplies. Power supplies can generally be operated from a wide input voltage range. We will answer how this is possible. Let's compare this feature with the resistive dividers characteristic used in the last example. For a 7-volt input, 2.83 volts appear on its output. Connecting 35 volts to its input will result in output voltage of 14.16 volts. The first one is not enough to light up the LED, however the second one may ruin it. You can check these output voltages with your own calculations based on what you learned in the previous video. It is important to note that the voltage at the output is unfortunately also dependent on the input voltage if there is no regulation on the supply. We will see the regulation soon, but first let's move on to the efficiency of the power supply. The efficiency of the power supply is also important. It shows how effectively the power supply can produce the output voltage from the input voltage. This efficiency is defined as the ratio of the output and the input power. Efficiency of a good power supply is approximately 100%, i.e. the output power is almost the same as the input power. In case of a device which is battery powered, the efficiency is particularly important. Let's compare how long a device can operate from a battery using two different efficiency power supplies. In the diagram, you can see the input and output power, and we also have another figure with the time diagram. For example, if we would like to charge our phone with 1 amps of current and 5 volts of voltage, then it will mean 5 watts of power consumption. This is a charger with 90% of efficiency. As you can see in the formula, the input power is given by dividing the output power with the efficiency. So I divide 5 watts by 90%, which gives that 5.56 watts of power should be drawn by the power supply. In comparison, the much worse 50% efficiency charger's formula is P out divided by the efficiency, that is 5 watts divided by 50%, so it needs 10 watts to power. If we operate the chargers from a 12 watt-hour battery, then the first power supply will be able to operate for 2.16 hours. In contrast, the other will be able to operate for only 1.2 hours, so in the second case, we can charge our phone less. Let's see how we got these durations. 2.16 hours were calculated by dividing 12 watt-hours by the power input of 5.56 watts, and 1.2 hours by dividing 12 watt-hours by the power input of 10 watts. So we can see that for energy saving, it is important that the efficiency is as close to 100% as possible. In this ideal case, which of course does not exist in reality, the energy consumed by the power supply would appear on the output without any loss.
And what happens with the loss? Where does the energy go if it's not the output?
Excellent question, and very important too. Efficiency is not only very important for energy saving. The power supply converts losses mainly into heat, in other words, it dissipates them. A power supply with 90% efficiency, for example, converts the remaining 10% of the energy into heat, while a power supply with 50% efficiency converts 50% of the input energy into heat. This means that for the same power input, our power supply will heat up 5 times more in the latter case. And the heat generated has to be dissipated somehow. For large amounts of heat, water cooling may be necessary, but an aluminium heatsink will usually do. In this case, the heatsink transfers the heat to the air. Going back to the resistor divider set up in the previous video, it's important to note that a large amount of power is dissipated on resistor R1, so the efficiency of this resistor divider solution is very poor.
Now we know the basic characteristics of power supplies. In our next video, we will finally put together a regulated power supply. Stay tuned for more. Goodbye.
Bye bye.